Assalamualaikum and hello everyone, and especially Dr. Herman. We are from Group Set 2, and today we will be presenting our case study on the traction drive system. My name is Mos, and I am joined by my teammate, that is Samsuri, Daniel, and Siwan. Our objective is to accurately position a machine table. The system uses a traction drive motor with a capstan roller with offer low friction and no backlash compared to traditional ball screw. However, because it is susceptible to the disturbance, we need to design a rhombus control system. We'll walk you through the modeling analysis and controller design phase of this project. I will pass over to Samsuri.
Thank you, Moss. To begin our analysis, we first had to derive the open loop transfer function. As you can see on the screen, the system consists of a DC armature control motor where the driver bar moves a linear slide table. Based on the block diagram in figure 2, we identified three main stages. The electrical component represented by the gate Km over the impedance. The mechanical component defined by total inertia, JT and motor damping. The output stage where the angular velocity is integrated to find position and multiplied by the roller radius. By applying the feedback law for the back EMF loop, we can mathematically prove that the transfer function match the model provided in our assignment. And now I will pass to Daniel.
Thank you, Shamsuri. I will now discuss the system analysis. For part B, we implemented a unity feedback loop with a gain K. Using the parameter from table 1, such as the motor resistance of 1.36 ohm and motor inductance of 3.6 millihenry, we simulated the response in MATLAB. Our initial time domain analysis focused on first, stability, determining if the system remains steady under gain K. Second, performance metric. We measured the peak time TP, settling time TS, percentage overshoot, percent OS, and steady state error ESS. And the third one, finding. We found that while the system is functional, a simple gain K often results in a trade-off between speed and high overshoot. Thank you. I pass to T1.
Okay. To improve the performance, we designed a PID controller using the root locus method. Based on the linear analysis, we set a specific design goal to reduce the settling time and minimize overshoot. Our design process involved theoretically calculation the pull and the zero required to pull the root locus into the desired region. Implementation. We modeled the PID controller in our simulation to observe the output response. And the result, the PID controller successfully eliminate the steady state error and allow the side table to reach its target position with a much higher precision.
In addition to the PID, we also designed a lead compensator using the block part method. This was done using the same design specification we used for the PID. Next.
Through theoretical calculation, we determine the necessary phase lead to improve the system phase margin. When we compare the three setup, unity feedback, PID, and lead compensator, unity feedback was the simplest but had the poorest performance. PID provided the best error elimination and response speed. Lead compensator offer improved stability and high frequency performance.
So,
And now,
in
Daniel, for
conclusion,
the conclusion.
oh sorry. So in conclusion, our case study demonstrates that while traction drive has superior friction characteristics, they require sophisticated control to handle their sensitivity to disturbances. P1,
A- And
yes.
by applying both root locus and the frequency response method, we have successfully optimized the traction drive system to accurate table position. Thank you for your time, and we now open the floor for any question. Thank you.